Hey, what's up, cyber warriors? Welcome back to Skillshetra, your battlefield for hacking skills, knowledge, and capture the flag victories. I'm your host Kushal, and you're watching episode 10 of our Hacker101 CTF walkthrough series. And trust me, it's a juicy one. Today, we're cracking open model E1337, the rolling code lock, a challenge that'll twist your logic, sharpen your eyes, and elevate your exploit game to the next level. If you've ever wanted to learn how to decode time-based logic, spot subtle clues in obfuscated code, and roll your way into a system like a pro, buckle up because we're diving deep. So grab your coffee, fire up your terminal, and let's break some code. Let's roll. To get this first flag, we have 3 hints. Hidden functionality is good. Functionality: comments can often reveal important things. XML from untrusted sources must be processed carefully. I began doing some directories reconnaissance. While doing that, I navigated to /admin, which exposed the following page. The HTML comment caught my attention. It mentioned getConfig, which I tried but did not gather much information. But that getConfig path hinted that there might be a setConfig endpoint as well. I tried it out and got a generic 400 bad request response. This kind of error often means the server was expecting a specific format or type of data, such as structured input like XML or JSON, and the browser didn't send it correctly. Since the endpoint name was setConfig, it suggested that the server might be accepting configuration data, possibly in XML format. That's where XXE vulnerabilities come into play. And it was a solid lead worth testing. I decided to test for XXE vulnerabilities, and after a couple successful attempts to confirm that the page was indeed vulnerable to XXE attacks, I crafted the following payload. This uses the XXE entity, which causes the parser to insert the contents of /etc/password here when the XML is processed. This defines an entity XE that tells the XML parser to load the contents of main.py, assumed to be in the same directory where the XML is being passed. When parsed, this gets replaced by the contents of main.py. This redirects us to admin page, and when we see source code, we get our first flag. So here are the checks we have so far. Confirmation of XXE vulnerability. This confirmed that the setConfig endpoint was passing XML and was vulnerable to XML external entity XXE injection. My payload worked exactly as intended. The entity I defined was expanded and injected server-side. Source code disclosure. Even more importantly, the content of main.py revealed the internal server logic, including the use of the rng.py module. A comment in the code showing the first flag, a critical function that checks user input against a value produced by next26, implying a pseudo-random number generator, PRNG, was being used for the unlock code. In the import section of main.py, I saw from rng import all. This meant that the logic generating the unlock code wasn't in main.py but in a separate file. rng.py. Immediately I realized if I wanted to reverse or predict the unlock codes and get the second flag of the challenge, I needed to leak and analyze the contents of rng.py. I reused the same XXE payload, but this time swapped main.py for rng.py. When loaded, the source code for rng.py appeared in the source code of the admin panel, and it revealed a custom pseudo-random number generator, PRNG. The PRNG uses a non-standard custom implementation seeded with a 32-bit value. Here's what matters. Setup seed initializes a global variable state using bitwise operations to inject complexity. Next bits generates a number by shifting state and applying further bit level mutations. The function next26 was used in main. To produce the correct unlock code. This meant to find the correct unlock code, flag 1, I needed to reverse this PRing. I wrote code PRing tracker. Purpose of the PRing tracker. This class is designed to observe the outputs of a PRing, reconstruct its internal state using bit dependency tracking, use linear equations over GF2 binary field math to solve for the internal state, predict future outputs of the PRing deterministically. The init function initializes the tracker with the following: RNGH3s, the random numbers generated by the PRNG that we have observed. NB8, each number has 26 bits. Number, total number of random numbers observed. State, A, a symbolic representation of the internal PRNG state. 64 symbolic bits. All on ret, storage for the symbolic expression of each output bit. Initialize state A function sets up the initial PRNG state where each bit is symbolically tracked. Each of the 64 bits is initialized to a unique index of 63 minus I key, so we can track them individually. Getran bit track function. This is where the magic happens. Models the PRNG's update rules, tracks how each output bit is formed by applying bit shifting, state evolves forward. XOR with a reserved constant. Nonlinear substitutions, 4-bit nibbles, are transformed based on a fixed pattern. Returns the symbolic expression for the next output bit. This builds the list of expressions, all ret, that tell us which internal state bits influence each output bit. Solve the XOR function. Solves the set of equations of the form bit expression equals output bit, where bit expression is a set of symbolic bits using XOR. An output bit is a known bit from the PRNG output. It performs Gaussian elimination to eliminate variables step by step, like solving linear equations, remove contradictions or redundant equations, get a clean list of equations relating symbolic variables to actual bits. Decompose equivalent function. Given a new symbolic expression, this function tries to express it as a combination of the known solved equations, uses the same kind of raw reduction logic, Gaussian elimination, outputs which known equations by index can be XORed to form the target expression. Run function. This is the main method that does everything, converts all input numbers to a flat list of bits, runs the PRNG for the same number of bits, tracking symbolic expressions for each bit. Builds and solves a system of equations relating symbolic expressions to known output bits. Uses this solved state to generate the next output bits symbolically, decompose them into known combinations, XOR the actual bit values to compute the predicted number, returns the predicted random number as an integer. You can find this code in my description. And boom, that's how you defeat the model E1337 rolling code lock like a true cyber ninja. If you learned something awesome today, smash that like button, hit subscribe, and ring that notification bell so you never miss a CTF mission with me, Kushal, here on Skillshetra. Got questions, theories, or a crazy way you solved this challenge? Drop it in the comments. I'd love to hear from my fellow hackers. And hey, if this is episode 10, you know we're just warming up. More elite walkthroughs are on the way, so stay locked in. Until next time, keep hacking, keep learning, and remember, skills pay the bills. This is Skillshetra. Peace out.